My name is Khoo and this is my teammate.
Hi, my name is Ying.
Ordinary differential equation, also known as ODE. What is ODE? ODE is a differential equation containing one or more functions of one independent variables and the derivative of those functions. Importance of ODEs. ODEs play a crucial role in describing the behavior of dynamic system. Engineers use ODE to design control system, optimize processes, and predict system behavior under different conditions. Apart from that, ODE are used to calculate movement or flow of electricity, motion of an object, and also to model market dynamics and economic growth. ODE are essential for modeling and understanding dynamic system will change the course over time. The relevance of ODE spans numerous fields, including physics, engineering, biology, and economics, as they provide a framework for describing and predicting the behavior of complex systems. Key concept theories and laws. Differential equation, an ODE is an equation that contains one or more functions of a single variables and their derivative. Here is the example. Order of an ODE. The order of an ODE is the higher derivative present in the equation. For example, in this equation, we can see that the highest derivative is 2, so the equation is the second order ODE. Linear vs non-linear ODE. Linear ODE have solutions that can be added together to form new solution by using superposition principle. Non-linear ODE involves non-linear terms such as dy dx is equal to y squared plus x. Initial value problem. IPV specifies the value of the function and its derivative at a particular point. Boundary value problems. BVP specifies the value of the function at two different points. Separable equation. These ODEs can be written as the product of a function of xxx and a function of yyyy. Integration of both sides separately is needed for the method of solution. Exact equation derived from a single function. Homogeneous equations are solved by substitution. And the last one, second order linear ODEs, often involve a characteristic equation and methods like undetermined coefficient or variation of parameters. Here are the examples of mathematical notation and terminology. By understanding this concept and notation, we can approach solving ODEs systematically and apply them to a variety of practical problems.
Hi guys, so for this slide, I'm going to explain about the illustration of theories and laws. We have actually chosen 3 ODEs to be explained. The first one is separation of variables, and the other two is exact differential equation, as well as linear differential equation. The method of separation of variables involves rewriting a differential equation so that each variable appears on the different side of the equation, which allow it to integrate each side separately to find the final solution. Firstly, we should consider the first order ODE, which the equation appear to be dy dx equal to gx hy. Then, our goal is to rearrange the equation to separate the variables x and y. Once separated, integrate both sides with respect to their respective variables. For the last step is exponentiate both sides to solve for y.
While this graph acts as a visual aid for the example given, which is dy dx equal to xy.
The second one is linear differential equation. It is a first order linear differential equation which has the form dy dx plus pxy equal to qx. The solution involves finding an integrating factor ux. In order to solve the linear differential equation, we have to find the integrating factor mu x equal to e integration px dx. Second one, multiply both sides of ODE by mu x. Then we recognize that the left side is the derivative of mu xy. After that, we integrate both sides. Lastly, we get to solve for y. This graph is also ASM visual aid for the question dy dx plus y equal to e power x. Well, for the third one is exact differential equation. An exact differential equation is one that can be derived from a potential function fxy such that the equation mxy dx plus nxy dy equal to 0 can be written as df equal to 0. The potential function f satisfies d psi dx equal to mxy and d psi dy equal to nxy. For the first step, we have to verify the exactness. We will check if the given differential equation is exact by verifying that dm dy equal to dn dx. Second step is find the potential function psi xy. We integrate mxy with respect to x to find psi. Then we differentiate psi with respect to y and set it equal to nxy. Then we solve for hy by comparing the terms. After that, we write the solution. The solution to the differential equation is given by psi xy equals to c, where c is a constant. This is the example for exact differential equation. Next, for the first one, we are going to explain again about separation of variable. This example demonstrates the separation of variables method where the ODE is manipulated to allow integration of each side with respect to a single variable. The second one is exact differential equation. This example shows how to verify and solve an exact differential equation by finding the potential function whose total differential matches the given ODE. The potential function approach simplifies the process of solving the equation and provides a clear path to the solution. For the third one is linear differential equation. This example shows the method of solving first-order linear ODEs using an integrating factor, which simplifies the equation to an easily integrable form.
Next, we are going to talk about the application of ODEs, which is exponential growth. Exponential growth model describes how a population grows continuously and proportionally to its current size. So for the first question, we are going to find an equation to model the population. First, we shift the dt to the right side and we do the separation of variables. Then we get pt equal to 5000 e 0.04 t. For b, determine the population after 3 years. So the t is equal to 3 and we get approximately 5,637 people. And for the third question is, determine how long it will take the population to double. So since it's double, so we take 5,000 times 2 is equal to 10,000. So we take 10,000 equal to 5,000 e 0.04 t. Then we do the calculation and log both sides. And at the end, we get t approximately to 17.3 years. And t equal to ln 2 over k is also one of the equation for doubling time. Next is Newton's law of cooling. Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature, as well as estimating time of death in forensic science by measuring body temperature, which is as shown in the example below. So the equation is Tt equal to the surrounding temperature plus the difference between initial temperature of the body and the temperature of surroundings times e to the power negative kt, where k is a constant. So we sub 75, which is the temperature that cooled down during 7 p.m. and equal to 70 degree, which is the ambient temperature, plus the initial temperature of body, which is 80, minus the ambient temperature again, times e to the power negative k, and the t will be 60. At the end, we will get t equal to 90.59 minutes. And the time of death is 4:29 p.m. This is also a very common example for Newton's law of cooling. For the equation, we got dt dt equal to ktt minus tm, where k is a constant of proportionality, tt is the temperature of the object, and tm is the ambient temperature. First of all, we sub the ambient temperature, which is 10 Fahrenheit, and then we shift the dt to the right side. And then we do the separation of variables. And then we will get e power c equal to 60. And then we sub back the 60 to the e power c. Finally, we get k approximately to negative 0.8109 at t equal to 1 minute. We just sub 1 as t, and t1 minus 10 equal to 26.67. And for the reading of the thermometer at t equal to 1 minute is 36.67 Fahrenheit. And how long will it take to reach 15 Fahrenheit? So we use back the equation that we had found, which is tt minus 10 equal to 60e negative 0.8109 t. Then we sub 15 Fahrenheit for the tt, and we log both sides, and we get 3.06 minutes. Thank you.
In conclusion, we can know that ODE are fundamental in mathematics and have broad application in physics, engineering, biology, economics, and various other fields. The topic of ODE is vast and rich with application, and the scope of this video only scratches the surface. I encourage you to develop deeper into the study of differential equation, exploring more complex types such as non-exact equations, nonlinear ODE, and so on. Understanding this concept more can enhance your ability to model and solve real-world problems in various disciplines.